Thanks, John. I want to add my own thanks to the organizing committee and John and the other organizers of the Materials Mini Symposium. Material science is a field where I have been doing tool building in software for a number of years, and there are not a lot of fora where we can talk about sort of material science tools specifically. Materials conferences themselves tend to be mostly about the materials problems you're solving, and that is, of course, appropriate and correct, but it means that it's hard to talk about the kinds of things that I've been doing. So I've always loved the SciPy meeting, and being able to do material science, having a material science focus at SciPy is wonderful. I'm going to talk now about the tool that I have been building. Many years ago, I think in the late 90s, actually before my time at NIST, there was an attempt made to do finite element modeling of material microstructures. Those of you who know material science will know that if there is a theoretical foundation or axiom of material science, it is that structure controls properties. And the idea of being able to do structure property linkages in software seemed obvious, but it was in fact very hard. The available tools were poorly adapted. There were commercial finite element tools like Abacus and ANSYS which have mesh generating engines that have a lot of schemes that allow you to mesh regular shapes and to build combine blocks together into complicated combinations of elementary regular shapes, but actually starting from an image that is very irregular at many length scales and getting down to a mesh from there turned out to be very hard. And even when you did that, if you have multiple components, figuring out where to put the different components to actually model the structure was also hard. So work started then at that point on a materials-focused FEM tool, usually with I believe, although again I was not there, I believe the fateful saying was, how hard could this be, right? So we started doing it. We, the institution of NIST, started doing it. To fill this niche in the tool space with image segmentation tools, meshing of the microstructures, and extensibility to a wide class of constitutive models, which seemed like it would be high value. And so the images at the bottom of this slide are representative of the sort of cross-section of materials that you might have. I actually have forgotten what the second one is. The first one on the far left is silicon nitride. And the third one is sort of my favorite. It's actually a phase field simulation that sort of reminds me and us that materials, microstructural images don't have to come from micrographs. They can come from other computations. And the fourth image is an electronic device of some kind that is manufactured. But again, even when you manufacture materials, as those of you who do this certainly know, the structure is not always the design structure, and there are additional complexities. So the scope, I've sort of already described material science. The scope of the tool is sort of mesoscale samples. We're thinking about microns when we do it, but there's no actual length scale built into the tool. It encapsulates the mathematics of material science, and the idea is that the user doesn't have to be themselves an expert on computational methods or on how to choose the appropriate ways to do matrix operations or even how to do a mesh. The assumption is that they can recognize a good one, but they may not know how to generate a good one, and so we offer them tools to generate many and select a good one. And so the basic questions are the structure property questions of material science. For a given structure, how do the constituent properties control the aggregate properties? And for given constituents, what structures give good properties? That's, of course, the inverse problem of materials design and is very hard, but maybe a little easier with some good tools. So our idea initially of what the mathematics that we cared about was fairly basic. We think that most materials constitutive rules or materials equations are basically PDEs. There's a possibly second order time dependent part, a possibly dissipative first order time dependent part, and there's some kind of flux, and it has a divergence, and the divergence of that flux is equal to the applied forces or zero or whatever, and that's so without the phi dots and phi double dots, it's essentially static equilibrium for some flux, and with them, it's the time evolution of that, sort of time dependent PDE. And the thing in the white box is the constitutive rule, and material science domain experts know this. So the goal is to give them access to this and allow them to plug the different parameters that they know will be important for their problem into this and have the tool take care of the rest of doing the model. And so again, this is very abstract. The reason there's no indices on here is I'm being deliberately vague about the dimensionality of the various objects. They are whatever they need to be. So typical fields that you might solve for are displacement, temperature, or concentration, and typical fluxes that in more or less corresponding order is the stress goes with the displacement, and the heat flux goes with the temperature, and a chemical flux might go with concentration. And the mathematics, the finite element part is absolutely bog standard. We don't propose to innovate in the finite element space. The idea is you take the field you want to solve for and you rewrite it as a sum of field amplitudes at nodes times these shape functions, and then you do everything. Once you take that seriously as your field and you put it into the equation and you get the integral weak form of the equation. So that bottom equation with some a little bit specialized notation is basically a giant matrix equation. The left-hand sum integral multiplies the vector of phi i's that are the amplitudes of the functions of the shape functions that tell you how your field goes, and the second term is the index by j is this vector that tells you the forces may be zero. So this scheme encapsulates a great deal of material science, and from there we expose an interface to the user that allows them to build constitutive rules, including stock standard constitutive rules that we already know about that people are going to want. So there's multiple built-in properties, all of the different crystallographic variants of elasticity, some couplings, thermal expansion, and the interface uses standard material science nomenclature for a material science audience. The tool includes the ability to save and share properties. We had at one time an elaborate fantasy that a community would grow up around the OOF tool that would share properties that they had found to be particularly useful. That could still happen. Data sharing tools are getting better and better. For a couple of years ago, it started to seem a little ridiculous, but now it's starting to seem sane again. The tool is open source, so the ultimate, if you are a real expert at many levels, you can extend the tool yourself, download it, clone the Git repo, whatever. So Python is conspicuously useful here. It's a widely used language that's easy to get started in. So again, about the audience, the OOF user is an expert in constitutive rules, but in the basic case, we assume probably doesn't want to write code. So the workflow is you start from an image that you get somehow, either from a microstructure or from a simulation, stack the images into a voxel set. There's a number of tools for modifying the image. You can blur and despeckle, you can do edge detection, and the goal is you want to be able to get a segmentation. And again, there's a bunch of tools for selecting regions. You can burn, you can actually paint a segmentation onto the image if you want to identify constituent phases. And again, here the assumption is that the user will recognize a good segmentation when they see it, and be able to generate a large number of candidate segmentations easily using our tools. The next step is to overlay a regular space filling grid on this segmented image, and then we have a number of grid mesh manipulation tools that will modify the mesh so that it then comes into correspondence with the boundaries of the segmented image while retaining the space filling and regular character of the mesh. So you can bisect elements, you can move nodes around, you can do simulated annealing. There's a fictive energy that goes with the mesh where that is high for elements that have large or very large or very small aspect ratios that are sort of needle-like or plane-like. And the energy also is large for elements that span multiple segments in the image, multiple regions in the segmented image, and low for elements that are nearly spherical and low for elements that are homogeneous. So you can kind of play with the various different amplitudes in the energy and get yourself a quality mesh. And again, the OOF user is imagined to be able to assess the quality of a mesh reasonably well visually, but maybe not construct one. And so I guess the picture on the right is then a picture of the microstructure, the example microstructure with the meshing process completed and the matrix part removed for visualization. And then you can solve the system with your constitutive rules. You have the system can handle nonlinear constitutive rules. It can do time dependence, and it has a suite of sparse solvers that you can pick from. There's a local graphics window that allows you to interactively assess your data, and a PDF export capability for publication quality, so you can publish directly from the tool, the images that is. The tool will not write the manuscript for you. There are statistical tools to allow you to kind of figure out what's going on for average, standard deviation, minimum and maximum. This can be important, particularly for microstructure analysis, where you want to assess the value of a homogenization process. If you're using OOF as a homogenization tool to get aggregate properties, it's possible that for some microstructures, aggregate properties might be dominated by outliers within a particular microstructure, and so the min and max tools can be important for finding that. The output scheme is also extensible. If you do want to write code, you can add new output methods. And there is a direct data export capability if you have a more sophisticated analysis that you want to do. One of the puzzles that you face when tool building, particularly workflow, tools that have workflow chains like this, is sort of when to stop, right? Like we could keep writing additional analytical methods for the rest of our lives, but it's hard for us to assess their value, and of course we have better things to do, we think. So there's a conceptual framework that matches the object framework of the tool. A material is a collection of properties, and properties, as I think I discussed later, are mappings from fields to fluxes, and the fluxes are the things that are in equilibrium. There are images which are, so there's I really want a pointer. So the biggest box at the bottom there, the microstructure, is sort of like the document object if you're preparing a presentation or if you're doing writing a Word document in Word. It's the highest level sort of container, and it contains images, and you can have multiple images in a given microstructure. In case one image allows you to classify one phase and the other image allows you to classify another phase, you can do that. We break the finite element process up into two steps. There is a skeleton, which is just the finite element geometry that has the nodes and edges that connect the nodes but doesn't have the equations. It turns out that that's a convenient abstraction to use in order to, firstly, to be able to assess the quality of the mesh, and in order to be able to more efficiently or more rapidly do some of the operations in the absence of the sort of encumbrances of the mathematics. And then there is the mesh, which is the standard ordinary finite element mesh. It has all of the nodes and equations, and the elements have the appropriate degree and all of that stuff, and has boundary conditions. That's what you probably think of as an ordinary finite element mesh, those of you who are familiar with finite elements. So it has a GUI mode or a menu-based command mode. The GUI mode we think is fairly intuitive, with the caveat again that it's a material science audience that we're reaching for. So a lot of the terminology for the properties, for example, is material science terminology. A naive user may have some difficulty with it, but the naive user is not our target. There's also, as you can see in the green on black there, a text mode. You can load scripts. If you want to run your life's work in OOF, you can do it. There's also the matching structure. From the command line, there's a hierarchical menu of operations starting with OOF and oof.file, and you can see there's an example. So script is under the load menu, and load is under the file menu, and file is under the root of all of the menus, which is called OOF. When you use the GUI, it writes a script every time you push a button that runs one of these menu items. It writes the menu item into a log file, so you can do the workflow that you want first in the GUI and then rerun it from the script, and it will do the same thing. So the architecture is something of a historical artifact. We started this, I came to this project in around 2000, and the second version of OOF was started around that time. It's a mixture of Python and C++. The virtues of the various components are listed here, but the thing that I want to comment on is in particular the use of Swig. When we started this process, there was no such thing as NumPy. There was no such thing as SciPy. And so we were kind of on our own in terms of how to do things in high performance from a Python top level. And Swig was our answer, and it was a very good answer, but also a little bit of a trap. We found that Swig was moving pretty quickly, and that the different versions of Swig that were distributed in different tools, different Linux distributions, had different bug sets that were sometimes incompatible. So we wound up standardizing on a particular version of Swig, version 1.1, build 883. And having standardized on that, then sat out the evolution of the Swig tool until we got to the point where there was a little bit of a time bomb that was ready to go off because the Swig-generated code started throwing deprecation warnings on new compilers. So we actually, our solution to that, somebody mentioned in one of the earlier talks, supporting the tools you depend on. We totally did that with Swig. We basically forked Swig 1.1 build 883 and adapted it to be firstly specialized for only Python and C++. We threw away the rest of the different mappings that Swig does. And we fixed the we modified our version to fix the deprecation warnings, and now we package and distribute an updated, essentially backport of Swig 1.1883 along with the OOF tool. So when your projects live long enough, this kind of thing can happen. So some of the other things we depend on, again, some reflect a little bit of vintage. Sparselib++, slightly customized, is a C++ sparse matrix library. We've migrated from distutils from the predecessor was a multi-thousand line makefile, which I rather liked, but wasn't very portable, and various other pieces. Probably the most modern of these things now is VTK, which we depend on for 3D. An advantage of the Swig tool that we have appreciated many times is that we have the ability to move the Python and C++ language boundary up or down. If there's something that we use a lot that is not performance critical, that's turning into a maintenance headache, we can take it out of C++ and put it in Python. If there's something that we did in Python because it was easy and we didn't know how important it would be, and then it turns out to be performance critical, we can put it behind Swig and move it to C++. And we've done both of those at different times for different pieces. The tool takes object orientation extremely seriously. We've paid very careful attention to making the object structure map the problem structure for comprehensibility, for maintainability. This also facilitates moving the language barrier, the Python C++ language boundary, not barrier, up and down. If you have good object correspondence, then you can do that more seamlessly. And it possibly helps with future expansion, although this also turned out to be a little bit of a trap, which I will discuss in a minute or two. A number of users have actually successfully used OOF for parametric studies, where you build a mesh in the GUI, write a command line script, and then tweak the parameters in the command line script. So one of my collaborators, Stefanos Papanikolaou, has done this, and here is an example of what his script looks like. So this is a stock OOF script where he's then edited it and added the Python for loop there for T and Ts, and just runs that as many times as he needs to, writing out the appropriate output files. Going forward, we're very interested in integrating ourselves into some of these materials workflows that are coming out as part of the Materials Genome Initiative and the ChiMed project. We would like to be able to ingest their data formats and generate data formats that they can consume. We are kind of at the beginning of actually doing something about this instead of just thinking and talking about it. And the things we're looking at probably are Dream3D and HDF5. And I know there's a talk later in this session from the Materials Project. We're also interested in interacting with them, ingesting maybe property data from them directly, sort of from the OOF console. If you could click, I need this material, get me at the elastic properties, and bring them in. That seems like that ought to be doable. So I want to spend the last bit of the talk on a development focus. Our next steps forward are to do crystal plasticity. So crystal plasticity, let me tell you briefly what it is. I'm going to skip that one because I think these slides maybe are not in such a good order after all. So plasticity is typically in metals. What happens is if you push on a metal and you push hard enough, eventually what happens is it softens a little bit, gets a little bit easier to push, and then when you let go, not all of the deformation comes back. So that means you've pushed it so far that it's into the plastic regime. And there's a lot of models about what is going on in the system when that happens. And one of the things that is certainly true about this is that the major contributing factor is the movement of crystalline defects within the samples, particularly in the regime of metals, which is what we're mostly thinking about in this. And so it's coupled to the crystallography in a fairly close way. And it's also sort of, if you were going to do plasticity in OOF, because we already have sort of grain level resolution and we already have these meshes that access the microstructure at this kind of very fine level, and our elasticity is already sensitive to the orientation, it seems like an obvious step that we should do crystal plasticity, which includes the orientation sensitivity. So this cartoon is of classical plasticity, just the phenomenology of some of the deformation not coming back. And crystal plasticity is better described in this slide, where the figure on the right in particular is meant to convey the different responses of the same sample to the same load at different orientations. So our initial thinking was we have this really good architecture, so what we'll just do, it's going to be the constitutive rule is going to be the thing it was before with a dissipative part and an equilibrium part, plus some field-dependent and maybe non-analytic features, but the architecture will be able to absorb these reasonably well. So we started out, we talked to some plasticity expert, we hired a postdoc from Hopkins who is a very good expert from the computational mechanics community, and we learned that it's not going to be anywhere near that simple. The way that crystal plasticity gets from the idea that there are a bunch of dislocations into the continuum is through this kind of thing, which is called a Schmid tensor. The name doesn't matter. What matters is that the contributions to the plastic strain are what you get from some number of planes moving in a direction m, these planes whose normal is n, and there's an equation that tells you how much plastic strain you get from some number of those dislocations moving, and because it's continuum, the gamma dot there is just a continuous number. You don't know in general how many planes have slipped, but you know how much strain you get in this LP. The notation is not critical, but the LP is the contribution to it, and the gamma dot has how much gamma dot you get as a function of the load depends a lot on what has gone on before in the system, and this kind of history dependence, which we knew about, turned out to kind of break the architecture. The other thing is that there's an impedance mismatch between the communities. So most of the OOF developers have a background in physics. They have a pretty mathematical way of looking at the world. You can maybe get that from the kinds of abstractions that we focused on when we developed the tool. And we needed to talk to people from the computational mechanics community, and that community is very algorithm focused. They have this algorithm that does the right thing for plasticity, and so now we were faced with a challenge of getting that algorithm, finding the abstractions in the algorithm and getting them into our tool. And so this is the sort of meant to be a picture of that. You can see at the bottom of the white area, there are the equations that we had before, including the LP equation, and that sort of gamma dot equals f of s conceals a multitude of horrors of history dependence and profound nonlinearity, and the fact that you have to figure out what's going on with the plasticity during a time step at the same time as you're figuring out what's going on with the stress, and the way the computational mechanics community does it, as illustrated, attempted to be illustrated in the yellow box, is the divergence of the stress is done in what is called the current configuration, which is the actual lab space where the physics is real. We agree that that's the right place to do it, but that's not where we were doing it before, so that's another architectural change, and the light yellow box is the mapping between the stress that we were using and the stress that we need to use going forward. So the answer is it's hard, but we're going to do it anyways. We're going to try and incorporate all of these effects into the original code and continue to keep our much valued generality. We still want to allow easily pluggable plastic constitutive rules, and we still want to talk to a material science audience. The strategy so far is we're building prototype codes to explore the architectural issues which arise. And so the current status is we have a prototype Python code that settled our object structure for us. We think we have the good architecture. We have a C++ code now that is, so the difference between Python and C++, of course, is Python does memory management for you and C++ doesn't. So we have sort of data management and data transport issues to settle, and also the thing about where do you do the integrals, we've branched the main code, and we're doing that there. All of these things are moving together, and one day it's going to work. So this is the current set of releases. I will distribute my slides if anybody really wants to read all this stuff. This is the team. The list is basically, the top list is people who are working on it now. Shahryar Keshavarz in particular is our solid mechanics expert. And the other list, the second part of the list, is everyone who's ever had commit access to our repo. And you can check out the URLs at your leisure. Thank you. Yeah.
So you use this version of Swig, what year was this whole version?
It was the first version that we ever used.
So my question was, do you consider like loose Python?
We've looked at a number of alternatives.
Because back then, basically, it would do C++ inheritance and so on, and keeping the object class hierarchy the same, but that was like 10 plus years ago.
When we looked at Boost, we haven't looked at Boost lately. When we looked at Boost and Boost Python, it was also a fast-moving target, so it was hard to standardize. It looked like it didn't. I mean, our problem with Swig was we ended up having to package it because every distro had a different version that had different bugs, and Boost seemed to have the same problem. So we.
But you were using it for Python, right?
Yeah.
C++.
It was C++. Yeah, we used Swig to go from C++ to Python.
Were you keeping the object classes
As far as possible, yeah. I mean, so some of the inheritance doesn't exactly work the way you want, in particular if you have virtual classes, virtual functions in C++ based classes. If you get a base class pointer in Swig, you may not have access to the derived functions. But Swig has a very rich type map syntax, which we learned a lot about to solve some of those problems. Part of
So you haven't considered like changing that? No, Swig's gotten a lot better in the last.
Yeah, well, so Swig, we looked at Swig 1.3 really hard, I guess 5 or 6 years ago, and it still had the same moving target problem. I mean, the compiler was better and the code was better, but yeah.
This is all on just, you're not considering other languages?
No. And as I said, when we forked Swig, one of the things we threw out was anything that isn't C++ or Python we threw out of our fork, so.